Hi students. Welcome back. I promised Kim Shepard's coming back. It's just the order that we take them in. She'll be back shortly in case you're getting sick of me. I know I've probably been, 3 hours straight on these videos. We're now in lesson 7. We're in the second unit. This is a transition unit. What we're working towards is modeling data, doing inference, confidence intervals, hypothesis tests. So we're just going to glaze the surface here with 2 examples in this lesson 7. All right, so lesson 7, it's the difference between data and models. In the first unit, we looked at data. In practice, what happens, students? So statisticians, scientists, academics, business people, etc. Typically what they'll do, they'll formulate a research question, and once that research question has been formulated, what they'll do is they'll collect data to investigate their hypothesis. Okay, so this is what we've done so far. To answer questions, first what we need to do is collect our data. We learned different ways to collect data back in lessons 5 and 6. Usually the first step once we have our data collected is to graph it. Way back in lesson 2, we did graphing. And finally, we will analyze or summarize the data. Lessons 3 and 4, we calculated summary statistics. So we'll put summarize here. This is what we've done. Collect your data, graph it, summarize it. Now we're taking that next step. We'll start to look at creating a model for your data and going into confidence intervals and hypothesis testing. Get this erased here. Most often, we learned about this a few lessons ago, most often researchers only get to use a small portion of the data, right? We only use a sample. Most often researchers must utilize only a sample of the data contained in the whole population. Remember, population's the big group. We're always interested in the big group. But collecting data costs money, collecting data takes time. So we will use statistical methods and just use a small piece, a sample. So for example, I'm not sure if this is in the notes or just on the slides, but if the state of Maryland was investigating the percentage of its residents that might take advantage of a tax break if they installed solar power grids on their homes, the state could certainly not reasonably expect to survey all 5 million plus Maryland residents. Just think about that project, trying to collect data from everybody that lives in the state, over 5 million people. So certainly they're interested in everybody, the population, but we'll have to take a sample and use the sample data to make a decision about the whole population. All right. Here's what statisticians and researchers often do. Once you have your data in hand, a lot of times the next step is to create a model using your data. What a model is, it's usually a mathematical formula. A model is a mathematical, the word here is generalization. A model is a mathematical generalization of the pattern represented in the data. So we collect our data and we try to generalize. What's the data telling us in a broader scope? Okay, so I do have an example on the next slide. I know this one's not in the notes. Hopefully the camera can pick up the graph. All right, here's this example. Data was collected, say we manufacture an electronic component, something that goes in a computer, a little chip or something. And the variable measured was time until failure. So maybe this component's in the design stage and engineers are running tests, how long till this thing blows out. I've got the data's in the histogram here, all the blue bars, and you can see most of these components are blowing out very quickly. This is time until failure, measured in minutes. So just so you can pick this up on the video, 0 minutes, 10 minutes, 20 minutes. Here's the data. Maybe they ran there's quite a bit here, this is 200, so maybe 175 here, plus, plus, plus. Maybe they ran 300 or 400 tests. what an engineer might want to do is sort of summarize what the data is telling us, and they would make a model. So there's a line here. I'm going to draw it in black so we can pick it up on the video, but I could represent this with a mathematical equation. So you think back to your functions in algebra class, f of x equals something, right? And this, I don't know what it would be, but I'll just, blah, blah, blah. That's what we're talking about. This is a model. We see the pattern in the data, and now we want to sort of generalize and come up with a mathematical equation or a function that tells us what the data is telling us. Okay? So keep in mind the difference. Data, blue histogram, model is going to be that smooth curve. Okay? Now this particular model we don't cover in Math 127, but there are two that we'll cover extensively. One's a normal model, and the other is a straight line model, linear regression. Okay, so I believe in this video, yep, this is the normal model. All right, pretty much everybody's familiar with IQ scores, so here's the example. 385 Ivy League undergrads were recruited to take part in an IQ study. The head researcher theorized that Ivy Leaguers are more intelligent than the general population, than the typical person. So you might know this. The average IQ is set at 100. So here's what they did to collect the data. At each of the 8 Ivy League schools, 50 students were randomly selected. So 50 came from each school, and they were given a $100 prize to participate, get them out of bed on a Saturday morning, come take an IQ test. Due to the incentive, there wasn't much non-response. I guess 15 students slept in. So what do we have? 400, maybe 385 data points. And below are just the first few rows of the data set from StatCrunch. And this is in the notes. There would be 385 in total. You can see in your note packet, right, the first student had an IQ of 90, second student had an IQ of 110. Here's a 58, maybe the student just blew off the test, or who knows what. Here's 129, and so on. So that's the data. All right. Let's review just a few quick things. What kind of sampling methodology was used? Explain. So let's think about this. We took the Ivy League, we broke it into the 8 schools, and then we took a simple random sample from each of those 8 schools. So this is what? This is stratified by school. Okay, we look at the schools as groups that might be different, so we just take, 100 or 50 students from Harvard, 50 students from Yale, 50 from UPenn, etc. So sampling methodology that was used, stratified by school. Right? Pick 50 randomly at each school. Part B, let's make sure everybody knows what we're talking about. What exactly is the data? It's simple, but write it down. This is just the list of, I think we had 15 sleep-ins, so 385 IQ scores. By now, you've used StatCrunch in class many times. This is the data. It's a list of numbers. We want to start to analyze this data using the things that we know how to do. Okay? Question, I guess there's a C here. What exactly is the population of interest, and what is the sample? All right, population of interest. Population. This would be all Ivy League undergrads. Every last one of them. And curiosity got the best of me. I looked up how many are there, and the answer is 126,000. Truth be told, there's probably graduate students in here, so knock out the graduate students, and maybe it's 100,000 undergrads, but this would be very expensive, very time-consuming to give 100,000 students an IQ test. So we're just going to work with the 400 that we tried to sample. Okay, that's the population. Out of this population, we took that sample. Sample is sort of like the data, right? Sample is just the 385 that were selected. All right, so pretty easy here. Data would be the exact data values that you have, but the samples collectively, that group that we took from the population. All right, so we're working towards modeling. We should look at pictures of the data. We should start calculating summary statistics. Well, here we go. Researchers then looked at the data. They summarized it as follows. So this is in the notes. So you can see the scale and everything. Here's a histogram, 385 IQ scores. Here's 100, right? We know how to describe data. This is certainly a unimodal. There's one peak. This is very symmetric. And now what we're going to start doing is say, all right, can I generalize what's going on? That smooth curve seems to generalize the pattern. It's not perfect, right? I guess I have a couple extra students here, maybe a little hole here. But in general, this smooth curve is doing a pretty good job of describing what's happening. This is a model. I could write this as a mathematical equation, though it's sort of beyond the scope of this course, right? So the smooth curve is a model. There's the smooth curve. I guess we're going to sort of get this out of here. Researchers ran the summary statistics. The main point of the study was our Ivy League undergrads smarter than average when it comes to IQ. A couple important points here. 385 students. Looks like their average IQ was 102.57. That's a bit higher than 100. 100 is general population. Students watching the video, does this convince you that Ivy Leaguers have a higher IQ score? Right? This is where we're going in this class. Here's a standard deviation. It looks like 15 right on the nose. I threw in some percentiles here as well, but you know, these three numbers here, sample size, mean, and standard deviation, are pretty much the three ones that we're going to start to work with again and again and again. All right, flip over that page. Researchers at this point might ask themselves a question. If Ivy League students really had an average IQ of 100, just like the general population, how unlikely would it be for us to take that sample of 385 of them and get that sample mean of 102.57? So suppose Ivy Leaguers are just like general population. Could that happen, or is that evidence that they have a higher IQ on average than the rest of us, right, the general population? Okay, this is sort of a little intro to hypothesis testing, which is where we're going at the last part of the course. Okay, I have the two models. Looks like you've got them in your note packet as well. There's an important slight difference here, and it's really hard to see it on this projector screen, but researchers at this point might try to draw that smooth curve, right, that model that describes the general distribution of IQ scores. The smooth curve is the model. It could be written with a mathematical equation beyond the scope of the course. On the left here, I drew in that model that's centered at 100. You can see it in your notes much better, but let me put it in black here. Here's the model centered at 100, and can you see that this model might not necessarily fit Ivy League? The blue, the data, seems to be just shifted ever so slightly. Okay. On the right, I ran a second model. This is the one where the mean is 102.57. And I just put that there. You can see it in your notes. And very close, right? These are two different models. This is a normal curve. We'll be working with this extensively. And this one is sort of centered on the data, whereas this one over here I put at 100 as the center, and the data seems to be just shifted up ever so slightly. Okay, so you can have a lot of different models. And in fact, a lot of upper level statistics and mathematics is picking the best model. Like once you have your data, let's pick the best model to summarize what's happening. All right. As you can see, neither model is perfect, right? Both models are imperfect. Models are just generalizations, so they will be, I said wrong, right? Yeah, the models will be wrong. Hopefully not by much. I mean, maybe squeeze that in there, right? P.S. Models will be wrong, hopefully just not by much. We just hope for our models to be useful. We'd like to use models to make predictions, okay, to run hypothesis tests. We just hope for our model to be useful. All right. Flip the slide, we're still on the same page. A big part of statistics is choosing the best model, like I said. With the data collected by the researchers, the model on the right, this one here centered at the 102.57 is probably a better choice. But there's something that we need to think about at the bottom of the page there. Realize this. If the researchers were to collect new data, by the way, they won't. You'll take one sample and you have to use the sample to the best of your ability. But if you threw back the 385, woke up 385 new students next Saturday at the Ivy League schools, you'd get different data. The histogram would change, probably slightly, but it would. The summary statistics would change, right? The summary statistics would very likely be different from what we originally collected. This would probably lead to a different model. So again, all models are wrong. You collect good data. And if you collect good data, hopefully you can make a good, useful model. Okay? But we always realize that whatever model we choose is probably not perfect. Okay? So I think there's a few questions here on the next couple pages. And then we'll look at linear in the next video. What are models good for? Found my picture of a fortune teller here on the internet, so that's, I don't know if the video is picking that up or not, but that's what that is. What are models good for? One answer is prediction, right? The answer is prediction. Let's see if that's my answer in the notes. Good. I like the way that I think. If the model is good, put it in quotes, it's sort of a generic term, right? If the model is good, our predictions should be good. Good models come from good data, and we know how to collect good data. We should use simple random sampling, but we have other methods to collect good data as well. 3 questions, then we're done with this transitionary video here into the fun part of the course. Question 1, presuming that the normal model, the one centered at 102.57, is a good model, what percentage of all Ivy League students should we expect to have an IQ exceeding 100? So let's repeat that so we understand. We're going to pick that model centered at 102.57, and I'd like to answer this question. What percentage of all Ivy Leaguers would we expect to have above average IQs? And the average is 100 for the general population. In a few lessons, we'll be able to answer that question. On StatCrunch, there's a calculator. It's actually sort of impossible to calculate this by hand, so we'll have to rely on technology. But I have a model here. This model, write yourself a note. This model is centered at 102. 0.57, even though the computer put this 100 right here and sort of labeled it 60, 80, 100. You might think it's centered at 100, but it's not. So 102, I just put a line right there. There's your 102, 57. What percentage of Ivy Leaguers would we expect to have IQs 100 or bigger? Here's a normal model I would actually shade from 100 and up. The calculator, or excuse me, StatCrunch will handle it. And so here's the answer. Our model is telling us that about, 56.8% of all Ivy Leaguers. That makes sense that that's more than half the population of Ivy Leaguers, right? If they're in the Ivy League, I'd expect them to have pretty high intelligence in general. So common sense has to kick in. If our model told us, well, 100% or 98% or something, we might question our model, but this could be reasonable. All right, this could be reasonable. Flip over one more question. Let's see what this one says here. Next page, presuming the normal model, that one centered at 102.57 is still good. What's the IQ score that marks the 95th percentile? So in other words, if I'm looking at Ivy Leaguers, what IQ score marks the top 5%? Right? 95% puts the 95% at the bottom and then top 5%. So if you're in the Ivy League, you've got an exceptionally high IQ, what IQ is that? All right, we'll learn how to answer these. The point of this lesson is not how do you answer the questions, it's just what are the questions. Again, here's a normal model. Probably write this again. This is centered at 102.57. And, well, the way that we answer the question, I put 95% of the shaded stuff to the left. This would be top 5%. Right? As a decimal 0.05. Of course, we can go back and forth instantly. And let's see, the calculator on StatCrunch spits out the answer, and it tells us that it's 127.24. All right, so here's what our model's telling us. Our model's telling us that if your IQ is this high or higher, you're in the top 5%. Okay? These are normal model problems. It's in about 3 or 4 lessons. I forget off the top of my head, but we'll do plenty of these. So look forward to that because they're very important. Last one, probably the hardest question out of my 3, then we'll cut this video and move to something else. Flip the page, last page. Presuming, all right, so let's read this one slowly. Presuming Ivy Leaguers are no smarter than the typical American. In other words, Ivy Leaguers have an IQ of 100 just like the general population has an average IQ of 100, right? Their average is the same as the general pop. What is the probability that researchers, when they draw that random sample of 385 Ivy Leaguers, would actually get that sample mean of 102.57 or one even larger? All right, so think about it. This is the hard one here. If Ivy Leaguers are no different from the general population, what's the chance or what's the probability that we sample 385 of them and their average IQ is 102.57 or even larger than that? All right, so I'm just going to give you the answer here. We've got a little ways to go here. This is a lesson 18 problem. We're only on lesson 7, but I'd like to show you where we're going in this course, right? Take it on faith. The probability is approximately 0.0004. That's pretty unusual, pretty darn rare. If we think of that, let's see, that is about 4 in 10, 100, 1,000, 10,000, right? This is about a 4 in 10,000 chance. Well, it's about a 1 in 2,500 chance. Think about this one last time, then we'll cut the video. If Ivy Leaguers are no different than, well, the rest of us, what's the chance we go there on a Saturday and this happens? 102.57 average IQ, or even bigger. That's about 4 in 10,000 chance of happening, or about 1 in 2,500 chance. So what's that telling us? This data, the data that was collected, is it's convincing me, and soon it will convince you. This data is convincing me that, you know what, Ivy Leaguers do have a higher than average IQ. If I go to Ivy League schools, I can expect the average IQ to exceed 100. I don't know what it is precisely, right? But the conclusion is, based on this data, that at Ivy League schools, the average IQ exceeds 100. All right. So let that sink in for about maybe 4 to 6 weeks when we get to it. But these are the types of problems that we'll be answering. I think they're quite interesting, and I hope that you do too, because we're going to do a lot of them. All right? So thanks for watching, and we'll see you in class.